Chapter 10 Vector Algebra. Introduction. In our day-to-day life, we come across many queries such as what is your height? How should a football player hit the ball to give a pass to another player of his team? Observe that a possible answer to the first query may be 1.6 meters, a quantity that involves only one value, that is magnitude, which is a real number. Such quantities are called scalars. However, an answer to the second query is a quantity called force, which involves muscular strength, that is magnitude, and direction in which another player is positioned. Such quantities are called vectors. In mathematics, physics, and engineering, we frequently come across with both types of quantities, namely scalar quantities such as length, mass, time, distance, speed, area, volume, temperature, work, money, voltage, density, resistance, etc. And vector quantities like displacement, velocity, acceleration, force, weight, momentum, electric field intensity, etc. Some basic concepts. Let L be any straight line in plane or three-dimensional space. This line can be given two directions by means of arrowheads. A line with one of these directions prescribed is called a directed line. Now observe that if we restrict the line L to the line segment AB, then a magnitude is prescribed on the line L with one of the two directions, so that we obtain a directed line segment. Thus, a directed line segment has magnitude as well as direction. Definition 1. A quantity that has magnitude as well as direction is called a vector. A directed line segment is a vector denoted as vector AB or simply vector A and read as vector AB or vector A. The point A from where the vector AB starts is called its initial point, and the point B where it ends is called its terminal point. The distance between initial and terminal points of a vector is called the magnitude or length of the vector, denoted as modulus of vector AB or modulus of vector A or A. The arrow indicates the direction of the vector. Position vector. The three-dimensional right-handed rectangular coordinate system. Consider a point P in space having coordinates x, y, z with respect to the origin O, 0, 0, 0. Then the vector OP having O and P as its initial and terminal points respectively is called the position vector of the point P with respect to O. Using distance formula, the magnitude of vector OP or modulus of R bar is given by modulus of vector OP is equal to square root of x square plus y square plus z square. In practice, the position vectors of points A, B, C, etc. with respect to the origin O are denoted by vector A, vector B, vector C, etc. respectively. Direction cosines. Consider the position vector OP or vector R of a point P, X, Y, Z as in figure. The angles alpha, beta, gamma made by the vector R with the positive directions of X, Y and Z axis respectively are called its direction angles. The cosine values of these angles, that is cos alpha, cos beta and cos gamma, are called direction cosines of the vector R and usually denoted by L, M and n respectively. From figure, one may note that the triangle OAP is right-angled, and in it we have cos alpha is equal to x upon r is equal to r stands for modulus of vector r. Similarly, from the right-angled triangles OBP and OCP, we may write cos beta is equal to y upon r and cos gamma is equal to z upon r. Thus, the coordinates of the point P may also be expressed as LR, MR, NR. The numbers LR, MR and NR proportional to the direction cosines are called as direction ratios of vector R and denoted as A, B and C respectively. Types of vectors. Zero vector. A vector whose initial and terminal points coincide is called a zero vector or null vector and denoted as vector 0. Zero vector cannot be assigned a definite direction as it has zero magnitude, or alternatively, otherwise, it may be regarded as having any direction. The vectors vector AA, vector BB represents the zero vector. Unit vector. A vector whose magnitude is unity, that is 1 unit, is called a unit vector. The unit vector in the direction of a given vector, vector A, is denoted by A cap. Co-initial vectors. Two or more vectors having the same initial point are called co-initial vectors. Collinear vectors. Two or more vectors are said to be collinear if they are parallel to the same line, irrespective of their magnitudes and directions. Equal vectors. Two vectors, vector A and vector B, are said to be equal if they have the same magnitude and direction regardless of the positions of their initial points, and written as vector A is equal to vector B. Negative of a vector. A vector whose magnitude is the same as that of a given vector, say vector AB, but direction is opposite to that of it, is called negative of the given vector. For example, vector BA is negative of the vector AB and written as vector BA is equal to minus vector AB. Example 1. Represent graphically a displacement of 40 km 30 degree west of south. Solution. The vector OP represents the required displacement. Example 2. Classify the following measures as scalars and vectors. 1. 5 seconds. 2. 1000 centimeter cube. 3. 10 Newton. 4. 30 km per hour. 5. 10 gram per centimeter cube. 6. 20 meter per second towards north. Solution. Number 1. Time scalar. Number 2. Volume scalar. Number 3. Force vector. Number 4. Speed scalar. Number 5. Density scalar. Number 6. Velocity vector. Example 3. In figure, which of the vectors are 1. Collinear, 2. Equal, 3. Coinitial. Solution. Number 1. Collinear vectors, vector A, vector C and vector D. Number 2. Equal vectors, vector A and vector C. Number 3. Co-initial vectors, vector B, vector C and vector D. Addition of vectors. A vector, vector AB, simply means the displacement from a point A to the point B. Now, consider a situation that a girl moves from A to B and then from B to C. The net displacement made by the girl from point A to the point C is given by the vector AC and expressed as vector AC is equal to vector AB plus vector BC. This is known as the triangle law of vector addition. In general, If we have two vectors, vector A and vector B, then to add them, they are positioned so that the initial point of one coincides with the terminal point of the other. For example, in figure 2, we have shifted vector B without changing its magnitude and direction so that its initial point coincides with the terminal point of vector A. Then the vector A plus vector B, represented by the third side AC of the triangle ABC, gives us the sum or resultant of the vectors vector A and vector B. That is, in triangle ABC, we have vector AB plus vector BC is equal to vector AC. Now again, since vector AC is equal to minus vector CA, from the above equation we have vector AB plus vector BC plus vector CA is equal to vector AA is equal to vector 0. This means that when the sides of a triangle are taken in order, it leads to 0 resultant as the initial and terminal points get coincided. Now construct a vector BC dash so that its magnitude is same as the vector BC, but the direction opposite to that of it. That is, vector BC dash is equal to minus vector BC. Then, on applying triangle law from the figure 3, we have vector AC dash is equal to vector AB plus vector BC dash is equal to vector AB plus minus vector BC is equal to vector A minus vector B. The vector AC dash is said to represent the difference of vector A and vector B. Now consider a boat in a river going from one bank of the river to the other in a direction perpendicular to the flow of the river. Then it is acted upon by two velocity vectors. One is the velocity imparted to the boat by its engine and other one is the velocity of the flow of river water. Under the simultaneous influence of these two velocities, the boat in actual starts traveling with a different velocity. To have a precise idea about the effective speed and direction, that is, the resultant velocity of the boat, we have the following law of vector addition. If we have two vectors, vector A and vector B, represented by the two adjacent sides of a parallelogram in magnitude and direction, then their sum, vector A plus vector B, is represented in magnitude and direction by the diagonal of the parallelogram through their common point. This is known as the parallelogram law of vector addition. Properties of vector addition. Property 1. For any two vectors, vector A and vector B, vector A plus vector B is equal to vector B plus vector A, which is commutative property. Proof. Consider the parallelogram ABCD. Let vector AB is equal to vector A and vector BC is equal to vector B. Then using the triangle law, from triangle ABC we have vector AC is equal to vector A plus vector B. Now, since the opposite sides of a parallelogram are equal and parallel, from figure we have vector AD is equal to vector BC is equal to vector B and vector DC is equal to vector AB is equal to vector A. Again using triangle law, from triangle ADC we have vector AC is equal to vector AD plus vector DC is equal to vector B plus vector A. Hence, vector A plus vector B is equal to vector B plus vector A. Property 2. For any three vectors, vector A, vector B and vector C, in bracket, vector A plus vector B plus vector C is equal to vector A plus in bracket vector B plus vector C, which is associative property. Proof. Let the vectors vector A, vector B and vector C be represented by vector PQ, vector QR and vector RS respectively, as shown in figure 1 and 2. Then, vector A plus vector B is equal to vector PQ plus vector QR is equal to vector PR. and vector B plus vector C is equal to vector QR plus vector RS is equal to vector QS. So, in bracket, vector A plus vector B plus vector C is equal to vector PR plus vector RS is equal to vector PS. And vector A plus in bracket vector B plus vector C is equal to vector PQ plus vector QS is equal to vector PS. Hence, in bracket, vector A plus vector B plus vector C is equal to A plus in bracket vector B plus vector C. Multiplication of a vector by a scalar. Let vector A be a given vector and lambda a scalar. Then the product of the vector A by the scalar lambda, denoted as lambda into vector A, is called the multiplication of vector A by the scalar lambda. Note that lambda into vector A is also a vector collinear to the vector A. The vector lambda into vector A has the direction same or opposite to that of vector A, according as the value of lambda is positive or negative. Also, the magnitude of vector lambda into vector A is modulus lambda times the magnitude of the vector A. That is, modulus of lambda into vector A is equal to modulus of lambda into modulus of vector A. A geometric visualization of multiplication of a vector by a scalar is given in figure. When lambda is equal to -1, then lambda into vector A is equal to minus vector A, which is a vector having magnitude equal to the magnitude of vector A and direction opposite to that of the direction of vector A. The vector minus vector A is called the negative or additive inverse of vector A, and we always have vector A plus in bracket minus vector A is equal to in bracket minus vector A plus vector A is equal to vector 0. Also, if lambda is equal to 1 upon modulus of vector A, provided vector A is not equal to 0, that is, vector A is not a null vector, then modulus of lambda into vector A is equal to modulus of lambda into modulus of vector A is equal to 1 upon modulus of vector A into modulus of vector A is equal to 1. So, lambda into vector A represents the unit vector in the direction of vector A. We write it as A cap is equal to 1 upon modulus of vector A into modulus of vector A. Components of a vector. Let us take the points A, 1, 0, 0, B, 0, 1, 0 and C, 0, 0, 1 on the x-axis, y-axis and z-axis respectively. Then clearly, modulus of vector OA is equal to 1, modulus of vector OB is equal to 1 and modulus of vector OC is equal to 1. The vectors vector OA, vector OB and vector OC, each having magnitude 1, are called unit vectors along the axis OX, OY and OZ respectively and denoted by I cap, J cap and K cap respectively. Now consider the position vector OP of a point P, X, Y, Z as in figure. Let P1 be the foot of the perpendicular from P on the plane XOY. We thus see that P1P is parallel to Z-axis, as I cap, J cap and K cap are the unit vectors along the X, Y and Z-axis respectively. And by the definition of the coordinates of P, we have vector P1P is equal to vector OR is equal to ZK cap. Similarly, vector QP1 is equal to vector OS is equal to YJ cap and vector OQ is equal to XI cap. Therefore, it follows that vector OP1 is equal to vector OQ plus vector QP1 is equal to XI cap plus YJ cap and vector OP is equal to vector OP1 plus vector P1P is equal to xi cap plus yj cap plus zk cap. Hence, the position vector of P with reference to O is given by vector OP or vector R is equal to xi cap plus yj cap plus zk cap. This form of any vector is called its component form. Here, x, y and z are called as the scalar components of vector R, and xi cap, yj cap and zk cap are called the vector components of vector R along the respective axes. Sometimes x, y and z are also termed as rectangular components. The length of any vector, vector R is equal to xi cap plus yj cap plus zk cap, is readily determined by applying the Pythagoras theorem twice. We note that in the right angle triangle OQP1, modulus of vector OP1 is equal to square root of modulus of vector OQ whole square plus modulus of vector QP1 whole square is equal to square root of x square plus y square. And in the right angle triangle OP1P, we have modulus of vector OP is equal to square root of modulus of vector OP1 whole square plus modulus of vector P1P whole square is equal to square root of x square plus y square plus z square. Hence, the length of any vector, vector R is equal to xi cap plus yj cap plus zk cap is given by modulus of vector R is equal to modulus of xi cap plus yj cap plus zk cap is equal to square root of x square plus y square plus z square. If vector A and vector B are any two vectors given in the component form A1 I cap plus A2 j cap plus A3 k cap and B1 I cap plus B2 j cap plus B3 k cap respectively, then number 1, the sum or resultant of the vectors vector A and vector B is given by vector A plus vector B is equal to A1 plus B1 into I cap plus A2 plus B2 into j cap plus A3 plus B3 into k cap. Number 2, the difference of the vector A and vector B is given by vector A minus vector B is equal to A1 minus B1 into I cap plus A2 minus B2 into j cap plus A3 minus B3 into k cap. Number 3, the vectors vector A and vector B are equal if and only if A1 is equal to B1, A2 is equal to B2 and A3 is equal to B3. Number 4, the multiplication of vector A by any scalar lambda is given by lambda into vector A is equal to lambda A1 into I cap plus lambda A2 into j cap plus lambda A3 into k cap. The addition of vectors and the multiplication of a vector by a scalar together give the following distributive laws. Let vector A and vector B be any two vectors and k and m be any scalars. Then, number 1, k into vector A plus m into vector A is equal to k plus m into vector A. Number 2, k into m vector A is equal to km into vector A. Number 3, k into vector A plus vector B is equal to k into vector A plus k into vector B. Example 1. Find the values of x, y and z so that the vectors vector A is equal to xi cap plus 2j cap plus zk cap and vector B is equal to 2i cap plus yj cap plus k cap are equal. Solution. Note that two vectors are equal if and only if their corresponding components are equal. Thus, the given vectors vector A and vector B will be equal if and only if x is equal to 2, y is equal to 2, z is equal to 1. Example 2. Let vector A is equal to I cap plus 2j cap and vector B is equal to 2i cap plus j cap. Is modulus of vector A is equal to modulus of vector B? Are the vectors vector A and vector B equal? Solution. We have modulus of vector A is equal to square root of 1 square plus 2 square is equal to root 5 and modulus of vector B is equal to square root of 2 square plus 1 square is equal to root 5. So, modulus of vector A is equal to modulus of vector B, but the two vectors are not equal since their corresponding components are distinct. Example 3. Find unit vector in the direction of the vector vector A is equal to I cap plus j cap plus 2k cap. Solution. Vector A is equal to I cap plus j cap plus 2k cap. Modulus of vector A is equal to square root of 1 square plus 1 square plus 2 square is equal to square root of 1 plus 1 plus 4 is equal to root 6. The unit vector in the direction of vector A is equal to vector A upon modulus of vector A is equal to 1 upon root 6 into I cap plus j cap plus 2k cap is equal to 1 upon root 6 I cap plus 1 upon root 6 j cap plus 2 upon root 6 k cap. Example 4. Find a vector in the direction of vector 5 I cap minus j cap plus 2 k cap which has magnitude 8 units. Solution. Vector A is equal to 5 I cap minus j cap plus 2 k cap. Therefore, modulus of vector A is equal to square root of 5 square plus minus 1 square plus 2 square is equal to square root of 25 plus 1 plus 4 is equal to root 30. The unit vector in the direction of vector A cap is equal to 1 upon modulus of vector A into vector A is equal to 1 upon root 30 into 5 I cap minus j cap plus 2k cap, the vector with magnitude 8 units and in the direction of vector A. Therefore, 8 into A cap is equal to 8 into 1 upon root 30 into 5 I cap minus j cap plus 2k cap is equal to 40 upon root 30 I cap minus 8 upon root 30 j cap plus 16 upon root 30 k cap. Joining 2 points. If P1 Y1 Z1 and P2 X2 Y2. Vector joining 2 points. If P1 X1 Y1 Z1 and P2 X2 Y2 Z2 are any 2 points, then the vector joining P1 and P2 is the vector P1 P2 joining the points P1 and P2 with the origin O and applying triangle law. From the triangle OP1 P2, we have vector OP1 plus vector P1 P2 is equal to vector OP2. Using the properties of vector addition, the above equation becomes vector P1 P2 is equal to vector OP2 minus vector OP1. That is, vector P1 P2 is equal to X2 I cap plus Y2 J cap plus Z2 K cap minus X1 I cap plus Y1 J cap plus Z1 K cap is equal to X2 minus X1 into I cap plus Y2 minus Y1 into J cap plus Z2 minus Z1 into K cap. The magnitude of vector P1 P2 is given by modulus of vector P1 P2 is equal to square root of X2 minus X1 whole square plus Y2 minus Y1 whole square plus Z2 minus Z1 whole square. Example 1. Find the vector joining the points P, 2, 3, 0 and Q, minus 1, minus 2, minus 4 directed from P to Q. Solution. Since the vector is to be directed from P to Q, clearly P is the initial point and Q is the terminal point. So, the required vector joining P and Q is the vector PQ given by vector PQ is equal to minus 1 minus 2 into I cap plus minus 2 minus 3 into J cap plus minus 4 minus 0 into K cap. Therefore, vector PQ is equal to minus 3 I cap minus 5 J cap minus 4 K cap. Section formula. Let P and Q be 2 points represented by the position vectors vector OP and vector OQ respectively with respect to the origin O. Then the line segment joining the points P and Q may be divided by a third point, say R, in two ways, internally and externally. Here we intend to find the position vector vector OR for the point R with respect to the origin O. We take the two cases one by one. Case 1. When R divides PQ internally, take vector OP is equal to vector A, vector OQ is equal to vector B, and vector QR is equal to vector R. If R divides vector PQ such that M into vector RQ is equal to N into vector PR, where M and R are positive scalars, we say that the point R divides vector PQ internally in the ratio of M is to N. Now from triangles ORQ and OPR, we have vector RQ is equal to vector OQ minus vector OR is equal to vector B minus vector R, and vector PR is equal to vector OR minus vector OP is equal to vector R minus vector A. Therefore, we have M into vector B minus vector R is equal to N into vector R minus vector A. Vector R is equal to M vector B plus N vector A upon M plus N on simplification. Hence, the position vector of the point R which divides P and Q internally in the ratio of M is to N is given by vector OR is equal to M vector B plus N vector A upon M plus N. Case 2. When R divides PQ externally, we leave it to the reader as an exercise to verify that the position vector of the point R which divides the line segment PQ externally in the ratio M is to N, that is PR upon QR is equal to M upon N, is given by vector QR is equal to M vector B minus N vector A upon M minus N. Example 1. Find the position vector of a point R which divides the line joining two points P and Q whose position vectors are I cap plus 2j cap minus k cap and minus I cap plus j cap plus k cap respectively in the ratio 2:1, 1 internally, 2 externally. Solution. Number 1. A point R divides the line segment joining P and Q in the ratio 2:1 internally. Vector OR is equal to 2 into vector OQ plus vector OP upon 2 plus 1. Vector OR is equal to 2 into minus I cap plus j cap plus k cap plus I cap plus 2j cap minus k cap upon 2 plus 1 is equal to minus 2I cap plus 2j cap plus 2k cap plus I cap plus 2j cap minus k cap upon 3 is equal to minus I cap plus 4j cap plus k cap upon 3. The position vector of R is equal to minus 1 upon 3 I cap plus 4 upon 3 j cap plus 1 upon 3 k cap. Number 2. A point R divides the line segment joining P and Q in the ratio 2:1 externally. Vector OR is equal to 2 into vector OQ minus vector OP upon 2 minus 1. Vector OR is equal to 2 into minus I cap plus j cap plus k cap minus I cap plus 2j cap minus k cap upon 1 is equal to minus 2I cap plus 2j cap plus 2k cap minus I cap minus 2j cap plus k cap is equal to minus 3I cap plus 3k cap. The position vector of R is equal to minus 3I cap plus 3k cap. Example 2. Show that Points A, 2i cap minus j cap plus k cap. B, I cap minus 3j cap minus 5k cap. C, 3i cap minus 4j cap minus 4k cap are the vertices of a right-angled triangle. Solution. We have vector OA is equal to 2i cap minus j cap plus k cap. Vector OB is equal to I cap minus 3j cap minus 5k cap. Vector OC is equal to 3i cap minus 4j cap minus 4k cap. Vector AB is equal to vector OB minus vector OA is equal to I cap minus 3j cap minus 5k cap minus 2i cap minus j cap plus k cap is equal to 1 minus 2 into I cap plus minus 3 plus 1 into j cap plus minus 5 minus 1 into k cap is equal to minus I cap minus 2j cap minus 6k cap. Vector BC is equal to vector OC minus vector OB is equal to 3i cap minus 4j cap minus 4k cap minus I cap minus 3j cap minus 5k cap is equal to 3 minus 1 into I cap plus minus 4 plus 3 into j cap plus minus 4 plus 5 into k cap is equal to 2i cap minus j cap plus k cap. Vector CA is equal to vector OA minus vector OC is equal to 2i cap minus j cap plus k cap minus 3i cap minus 4j cap minus 4k cap is equal to 2 minus 3 into I cap plus minus 1 plus 4 into j cap plus 1 plus 4 into k cap is equal to minus I cap plus 3j cap plus 5k cap. Modulus of vector AB whole square is equal to minus 1 square plus minus 2 square plus minus 6 square is equal to 1 plus 4 plus 36 is equal to 41. Modulus of vector BC whole square is equal to 2 square plus minus 1 square plus 1 square is equal to 4 plus 1 plus 1 is equal to 6. Modulus of vector CA whole square is equal to minus 1 square plus 3 square plus 5 square is equal to 1 plus 9 plus 25 is equal to 35. Furthermore that modulus of vector AB whole square is equal to 41 is equal to 6 plus 35 is equal to modulus of vector BC whole square plus modulus of vector CA whole square. Hence, the triangle is a right-angled triangle. Product of two vectors. We may recall that product of two numbers is a number. Product of two matrices is again a matrix. But in case of functions, we may multiply them in two ways, namely multiplication of two functions pointwise and composition of two functions. Similarly, multiplication of two vectors is also defined in two ways, namely scalar or dot product, where the result is a scalar, and vector or cross product, where the result is a vector. Based upon these two types of products for vectors, they have found various applications in geometry, mechanics, and engineering. In this section, we will discuss these two types of products. Scalar or dot product of two vectors. Definition 2. The scalar product of two non-zero vectors, vector A and vector B, denoted by vector A into vector B, is defined as vector A into vector B is equal to modulus of vector A into modulus of vector B cos theta, where theta is the angle between vector A and vector B. 0 is less than or equal to theta is less than or equal to pi. If either vector A is equal to 0 or vector B is equal to 0, then theta is not defined. And in this case, we define vector A into vector B is equal to 0. Observations. Number 1. Vector A into vector B is a real number. Number 2. Let vector A and vector B be two non-zero vectors. Then vector A into vector B is equal to 0 if and only if vector A and vector B are perpendicular to each other. That is, vector A into vector B is equal to 0 double implies vector A is perpendicular to vector B. Number 3. If theta is equal to 0, then vector A into vector B is equal to modulus of vector A into modulus of vector B. In particular, vector A into vector A is equal to modulus of vector A whole square, as theta in this case is 0. Number 4. If theta is equal to pi, then vector A into vector B is equal to minus modulus of vector A into modulus of vector B. In particular, vector A into minus vector A is equal to minus modulus of vector A whole square, as theta in this case is pi. Number 5. In view of these observations 2 and 3 for mutually perpendicular unit vectors I, j and k, we have I cap into I cap is equal to j cap into j cap is equal to k cap into k cap is equal to 1. I cap into j cap is equal to j cap into k cap is equal to k cap into I cap is equal to 0. Number 6. The angle between two non-zero vectors, vector A and vector B, is given by cos theta is equal to vector A into vector B upon modulus of vector A into modulus of vector B, or theta is equal to cos inverse vector A into vector B upon modulus of vector A into modulus of vector B. Number 7. The scalar product is commutative. That is, vector A into vector B is equal to vector B into vector A. Two important properties of scalar product. Property 1. Distributivity of scalar product over addition. Let vector A, vector B and vector C be any three vectors. Then vector A into in bracket vector B plus vector C is equal to vector A into vector B plus vector A into vector C. Property 2. Let vector A and vector B be any two vectors and lambda be any scalar. Then lambda vector A into vector B is equal to lambda into vector A into vector B is equal to lambda into vector A into vector B is equal to vector A into lambda into vector B. If two vectors, vector A and vector B, are given in component form as a1 I cap plus a2 j cap plus a3 k cap and b1 I cap plus b2 j cap plus b3 k cap, then their scalar product is given as vector A into vector B is equal to a1 I cap plus a2 j cap plus a3 k cap into b1 I cap plus b2 j cap plus b3 k cap is equal to a1 I cap into b1 I cap plus b2 j cap plus b3 k cap plus a2 j cap into b1 I cap plus b2 j cap plus b3 k cap plus a3 k cap into b1 I cap plus b2 j cap plus b3 k cap is equal to a1 b1 I cap into I cap plus a1 b2 I cap into j cap plus a1 b3 I cap into k cap plus a2 b1 j cap into I cap plus a2 b2 j cap into j cap plus a2 b3 j cap into k cap plus a3 b1 k cap into I cap plus a3 b2 k cap into j cap plus a3 b3 k cap into k cap using the above properties 1 and 2 is equal to a1 b1 plus a2 b2 plus a3 b3 using observation 5. Thus, vector A into vector B is equal to a1 b1 plus a2 b2 plus a3 b3. Projection of a vector on a line. Suppose a vector AB makes an angle theta with a given directed line L, say, in the anticlockwise direction. Then the projection of vector AB on L is a vector P, say, with magnitude modulus of vector AB cos theta and the direction of vector P being the same or opposite to that of the line L, depending upon whether cos theta is positive or negative. The vector P is called the projection vector, and its magnitude modulus of vector P is simply called as the projection of the vector AB on the directed line L. For example, in each of the following figures 1 to 4, projection vector of AB along the line L is vector AC. Observations. Number 1. If P cap is the unit vector along a line L, then the projection of a vector A on the line L is given by vector A into P cap. Number 2. Projection of a vector A on other vector B is given by vector A into B cap, or vector A into vector B upon modulus of vector B, or 1 upon modulus of vector B into vector A into B cap. Number 3. If theta is equal to 0, then the projection vector of vector AB will be vector AB itself, and if theta is equal to pi, then the projection vector of vector AB will be vector BA. Number 4. If theta is equal to pi by 2 or theta is equal to 3 pi by 2, then the projection vector of vector AB will be 0 vector. Example 1. Find the angle between two vectors vector A and vector B with magnitudes √3 and 2, respectively, having vector A into vector B is equal to √6. Solution. Given that modulus of vector A is equal to √3 and modulus of vector B is equal to 2, and vector A into vector B is equal to √6. Let the angle between two vectors vector A and vector B be theta. Therefore, cos theta is equal to vector A into vector B upon modulus of vector A into modulus of vector B. Therefore, cos theta is equal to √6 upon √3 into 2. Therefore, cos theta is equal to √3 into √2 upon √3 into 2. Therefore, cos theta is equal to 1 upon √2 is equal to cos pi by 4. Therefore, theta is equal to pi by 4. Therefore, the angle between two vectors is pi by 4. Example 2. If vector A is equal to 5i cap minus j cap minus 3k cap, and vector B is equal to I cap plus 3j cap minus 5k cap, then show that the vectors vector A plus vector B and vector A minus vector B are perpendicular. Solution. We know that two non-zero vectors are perpendicular if their scalar product is 0. Here, vector A plus vector B is equal to 5i cap minus j cap minus 3k cap plus I cap plus 3j cap minus 5k cap is equal to 6i cap plus 2j cap minus 8k cap, and vector A minus vector B is equal to 5i cap minus j cap minus 3k cap minus I cap plus 3j cap minus 5k cap is equal to 4i cap minus 4j cap plus 2k cap. So, vector A plus vector B into vector A minus vector B is equal to 6i cap plus 2j cap minus 8k cap into 4i cap minus 4j cap plus 2k cap is equal to 24 minus 8 minus 16 is equal to 0. Hence, vector A plus vector B and vector A minus vector B are perpendicular vectors. Example 3. Find the projection of the vector I cap plus 3j cap plus 7k cap on the vector 7i cap minus j cap plus 8k cap. Solution. Vector A is equal to I cap plus 3j cap plus 7k cap. Vector B is equal to 7i cap minus j cap plus 8k cap. Therefore, vector A into vector B is equal to I cap plus 3j cap plus 7k cap into 7i cap minus j cap plus 8k cap is equal to 7 minus 3 plus 56 is equal to 60. Now, modulus of vector B is equal to square root of 7 square plus minus 1 square plus 8 square is equal to square root of 49 plus 1 plus 64 is equal to square root of 114. The projection of the vector A on vector B is equal to vector A into vector B upon modulus of vector B is equal to 60 upon square root of 114. Vector or cross product of two vectors. In section, we have discussed on the three-dimensional right-handed rectangular coordinate system. In this system, when the positive x-axis is rotated counterclockwise into the positive y-axis, a right-handed, that is standard screw would advance in the direction of the positive z-axis. In a right-handed coordinate system, the thumb of the right hand points in the direction of the positive z-axis when the fingers are curled in the direction away from the positive x-axis toward the positive y-axis. Definition 3. The vector product of two non-zero vectors, vector A and vector B, is denoted by vector A into vector B and defined as vector A into vector B is equal to modulus of vector A into modulus of vector B sin theta n cap, where theta is the angle between vector A and vector B. 0 is less than or equal to theta is less than or equal to pi, and n cap is a unit vector perpendicular to both vector A and vector B, such that vector A, vector B and n cap form a right-handed system. That is, the right-handed system rotated from vector A to vector B moves in the direction of n cap. If either vector A is equal to 0 or vector B is equal to 0, then theta is not defined, and in this case, we define vector A into vector B is equal to 0. Observations. Number 1. Vector A into vector B is a vector. Number 2. Let vector A and vector B be two non-zero vectors. Then vector A into vector B is equal to 0. If and only if vector A and vector B are parallel or collinear to each other. That is, vector A into vector B is equal to 0. Double implies vector A is parallel to vector B. In particular, vector A into vector A is equal to vector 0 or 0 vector, and vector A into minus vector A is equal to vector 0 or 0 vector. Since in the first situation theta is equal to 0 and in the second one theta is equal to pi, making the value of sin theta to be 0. Number 3. If theta is equal to pi by 2, then modulus of vector A into vector B is equal to modulus of vector A into modulus of vector B. Number 4. In view of the observations 2 and 3, for mutually perpendicular unit vectors I cap, j cap and k cap, we have I cap into I cap is equal to j cap into j cap is equal to k cap into k cap is equal to vector 0 or 0 vector. I cap into j cap is equal to k cap. J cap into k cap is equal to I cap. K cap into I cap is equal to j cap. Number 5. In terms of vector product, the angle between two vectors, vector A and vector B, may be given as sin theta is equal to modulus of vector A into vector B upon modulus of vector A into modulus of vector B. Number 6. It is always true that the vector product is not commutative, as vector A into vector B is equal to minus vector B into vector A. Indeed, vector A into vector B is equal to modulus of vector A into modulus of vector B sin theta n cap, where vector A into vector B and n cap form a right-handed system. That is, theta is traversed from vector A to vector B, while vector B into vector A is equal to modulus of vector A into modulus of vector B sin theta n1 cap, where vector B, vector A and n1 cap form a right-handed system. That is, theta is traversed from vector B to vector A. Thus, if we assume vector A and vector B to lie in the plane of the paper, then n cap and n1 cap both will be perpendicular to the plane of the paper, but n cap being directed above the paper while n1 cap directed below the paper. That is, n1 cap is equal to minus n cap. Hence, vector A into vector B is equal to modulus of vector A into modulus of vector B sin theta n cap is equal to minus modulus of vector A into modulus of vector B sin theta n1 cap is equal to minus vector B into vector A. Number 7. In view of the observations 4 and 6, we have j cap into I cap is equal to minus k cap. K cap into j cap is equal to minus I cap. And I cap into k cap is equal to minus j cap. Number 8. If vector A and vector B represent the adjacent sides of a triangle, then its area is given as 1/2 into modulus of vector A into vector B. By definition of the area of a triangle, we have from figure, area of triangle ABC is equal to 1/2 AB into CD. But AB is equal to modulus of vector B as given, and CD is equal to modulus of vector A sin theta. Thus, area of triangle ABC is equal to 1/2 into modulus of vector B into modulus of vector A sin theta is equal to 1/2 into modulus of vector A into vector B. Number 9. If vector A and vector B represent the adjacent sides of a parallelogram, then its area is given by modulus of vector A into modulus of vector B. From figure, we have area of parallelogram ABCD is equal to AB into DE, but AB is equal to modulus of vector B as given, and DE is equal to modulus of A sin theta. Thus, area of parallelogram ABCD is equal to modulus of vector B into modulus of vector A sin theta is equal to modulus of vector A into vector B. We now state two important properties of vector product. Property 3. Distributivity of vector product over addition. If vector A, vector B and vector C are any three vectors and lambda be a scalar, then number 1, vector A into in bracket vector B plus vector C is equal to vector A into vector B plus vector A into vector C. Number 2, lambda into vector A into vector B is equal to vector A into lambda into vector B. Let vector A and vector B be two vectors given in component form as A1 I cap plus A2 j cap plus A3 k cap and B1 I cap plus B2 j cap plus B3 k cap respectively, then their cross product may be given by vector A into vector B is equal to determinant I cap, j cap, k cap, A1, A2, A3, B1, B2, B3. Explanation: we have vector A into vector B is equal to A1 I cap plus A2 j cap plus A3 k cap into B1 I cap plus B2 j cap plus B3 k cap is equal to A1 B1 I cap into I cap plus A1 B2 I cap into j cap plus A1 B3 I cap into k cap plus A2 B1 j cap into I cap plus A2 B2 j cap into j cap plus A2 B3 j cap into k cap plus A3 B1 k cap into I cap plus A3 B2 k cap into j cap plus A3 B3 k cap into k cap by property 1 is equal to A1 B1 I cap into I cap plus A1 B2 I cap into j cap minus A1 B3 k cap into I cap minus A2 B1 I cap into j cap plus A2 B2 j cap into j cap plus A2 B3 j cap into k cap plus A3 B1 k cap into I cap minus A3B2 j cap into k cap plus A3B3 k cap into k cap, as I cap into k cap is equal to minus k cap into I cap. J cap into I cap is equal to minus I cap into j cap, and k cap into j cap is equal to minus j cap into k cap, is equal to A1B2 k cap minus A1B3 j cap minus A2B1 k cap plus A2B3 I cap plus A3B1 j cap minus A3B2 I cap, as I cap into j cap is equal to k cap, j cap into k cap is equal to I cap, and k cap into I cap is equal to j cap, and I cap into I cap is equal to j cap into j cap is equal to k cap into k cap is equal to vector 0 or 0 vector is equal to A2B3 minus A3B2 into I cap minus A1B3 minus A3B1 into j cap plus A1B2 minus A2B1 into k cap is equal to determinant I cap, j cap, k cap, A1, A2, A3, B1, B2, B3. B3. Example 1. Find modulus of vector A into vector B if vector A is equal to I cap minus 7j cap plus 7k cap and vector B is equal to 3I cap minus 2j cap plus 2k cap. Solution: vector A into vector B is equal to determinant I cap, j cap, k cap. 1 minus 7, 7. 3 minus 2, 2 is equal to minus 14 plus 14 into I minus 2 minus 21 into j cap plus minus 2 plus 21 into k cap is equal to 19 j cap plus 19 k cap. Therefore, modulus of vector A into vector B is equal to square root of 19 square plus 19 square is equal to 19 square root of 1 plus 1 is equal to 19 root 2. Example 2. Find a unit vector perpendicular to each of the vector A plus vector B and vector A minus vector B, where vector A is equal to 3I cap plus 2j cap plus 2k cap and vector B is equal to I cap plus 2j cap minus 2k cap. Solution: vector A is equal to 3I cap plus 2j cap plus 2k cap. Vector B is equal to I cap plus 2j cap minus 2k cap. Therefore, vector A plus vector B is equal to 3 plus 1 into I cap plus 2 plus 2 into j cap plus 2 minus 2 into k cap is equal to 4I cap plus 4j cap. Vector A minus vector B is equal to 3 minus 1 into I cap plus 2 minus 2 into j cap plus 2 plus 2 into k cap is equal to 2I cap plus 4k cap. Vector perpendicular to vector A plus vector B and vector A minus vector B is equal to vector A plus vector B into vector A minus vector B is equal to determinant I cap, j cap, k cap. 4, 4, 0, 2, 0, 4 is equal to I cap into 16 minus 0 minus j cap into 16 minus 0 plus k cap into 0 minus 8 is equal to 16 I cap minus 16 j cap minus 8 k cap. Now, modulus of vector A plus vector B into vector A minus vector B is equal to square root of 16 square plus minus 16 square minus minus 8 square is equal to square root of 256 plus 256 plus 64 is equal to square root of 576 is equal to 24. The unit vector perpendicular vector A plus vector B and vector A minus vector B is equal to plus or minus vector A plus vector B into vector A minus vector B upon modulus of vector A plus vector B into vector A minus vector B is equal to plus or minus 16 I cap minus 16 j cap minus 8 k cap whole upon 24 is equal to plus or minus 2 upon 3 I cap minus 2 upon 3 j cap minus 1 upon 3 k cap. Example 3. Find the area of a parallelogram whose adjacent sides are determined by the vectors vector A is equal to I cap minus j cap plus 3k cap and vector B is equal to 2I cap minus 7j cap plus k cap. Solution. The adjacent sides of a parallelogram determined by the vector A is equal to I cap minus j cap plus 3k cap and vector B is equal to 2I cap minus 7j cap plus k cap. Vector A into vector B is equal to determinant I cap, j cap, k cap. 1 minus 1 3, 2 minus 7 1 is equal to I cap into minus 1 plus 21 minus j cap into 1 minus 6 plus k cap into minus 7 plus 2 is equal to 20 I cap plus 5 j cap minus 5 k cap. Modulus of vector A into vector B is equal to square root of 20 square plus 5 square plus minus 5 square is equal to square root of 450 is equal to 15 root 2. Therefore, modulus of vector A into vector B is equal to 15 root 2. Therefore, required area of a parallelogram is 15 root 2.